The next speaker is Lionel Mason. Maybe I will introduce him because most of audience is from loop quantum gravity community. So actually Lionel was he was just about to complete his PhD, I think, when Ashtekar variables were formulated, and he wrote a fantastic paper together with Jacobson and a couple of other authors, in which they derived Ashtekar variables from self-dual two forms, and they showed relation, pointed out the relation between what we today know well as Plebański action. So they showed relation between the Plebański action and the Ashtekar variables. So that was very good completion to the Ashtekar derivation of his variables. So that explains the interaction with Lionel already a long time ago in the field of loop quantum gravity, which was about to be built on this. So the title of today's talk is, well, and Lionel is now very well known from Lionel wrote a book on applications of twistor theory to integrable models, but now he is very well known for calculating amplitudes. So this is probably what the talk is about. No. Okay, the title of the talk, scattering. Oh, sorry, scattering on. So the talk is on the gravitational waves going from one scry to another. Yeah, scattering on plane waves and the double copy.
Thank you very much. I mean, it's a great honour to come here and and to honour Jurek on his 60th birthday. It's a terrifying thing for me also because we're contemporaries, and that means that I must be getting somewhere close to that. But anyway, Jurek and I interacted a lot in our sort of early careers, maybe less so in recent years, and I have to be grateful to him for introducing me to one of my best students, and for a lot of which Maciej Jurekfest, who heard this morning, and Paweł Jurowski. I spent a lot of time with Paweł as well in the 90s. But we've veered off in different directions. We both had also an enthusiasm for CR manifolds and things algebraically special. So this talk will come back a little bit to some of that, although sadly to say, in maybe the most trivial case of a plane wave where there's no CR, no interesting CR structure. So what I'm actually going to do in this talk is to go off in a direction in which I think Jurek would be slightly allergic to, which would be to actually follow slightly more conventional lines towards constructing perturbative amplitudes on, but I'm going to do it on a curved space-time rather than on a flat space-time, something one has to do eventually. And plane waves are a good vehicle for this. As we know, they have a certain universality property in terms of being these Penrose limits. And but you can nevertheless compute on them. They have they satisfy this Huygens property that they admit sharp delta function solutions to the wave equation, and you can write them down. You can separate the Hamilton-Jacobi equations. And just as a kind of novelty in this, rather than just sort of blindly computing some things and saying, there you go, at the end, I wanted to test some ideas. In fact, our original motivation for this was to develop technology that we've been looking at, which I won't talk about, to do with ambitwistor strings for computing amplitudes, that they are much better suited to working on curved spacetimes than either Feynman diagrams or conventional strings. And so we wanted to develop that technology. And we needed data just to compare our computations to. And but the other thing which maybe this community is less familiar with is there's a lot of people getting excited by these double copy ideas. So I'll give you a brief introduction to that. These are ideas as to how it is you can express the output from gravitational calculations, their scattering amplitudes, as a double copy of those from Yangmills in a way that's rather different from other connections seen gravity in Yangmills that people have been studying before. So, in fact, what I'll do is I'll start with that double copy story, and I suspect that people here will be slightly sort of allergic to this as a kind of Feynman diagram-based approach to things. So I'll revert more to a sort of space-time based approach where I hope people will feel a bit more comfortable. So so for the double copy, we're in the world of momentum space and momentum space scattering amplitudes. And so the image is somehow that we're colliding a whole bunch of momentum eigenstates, and so they're coming in, they're doing something, and they're coming out again, and there could be many particles doing this. And to make life simple, we make them all plane waves for Yangmills. That's going to mean you have a polarization vector and ECI k.x and a color, an element of the Lie algebra of the gauge group. And by and large, once you've summed up all of your Feynman diagrams, you expect to get a scattering amplitude which depends on the momenta of all the particles that have come in. If it's tree level, there's no integrals. This is just a rational function of the momenta. And it's sort of multilinear in these polarization vectors. You've got n of these particles. It's linear in each of them. And similarly with the color factors. And so what you can do is you can hope to organize. So what color kinematics duality does is although the Feynman diagrams for Yangmills have cubic and quartic vertices, you hope to separate the quartic vertices and express it as a sum over trivalent diagrams where all of the kind of rational stuff is in the denominator, all of the fact that you have rational functions is encoded in sort of propagator factors in the denominator. So these will just be standard expressions of some of the momenta squared. And then the rest of this will just be a polynomial in k and epsilon and in the color factors. And now, although the Feynman diagrams don't come in a trivalent form for Yangmills, you can still nevertheless hope to organize them into this form by hand, perhaps. And so the C gammas is very straightforward. These are made out of structure coefficients for the gauge group, and so they naturally fall into trivalent diagrams. And what you can do is you can hope to get the kinematic factors to do so as well. And the basic idea of color kinematics duality is that the n gammas should actually share the kind of group theoretic properties of C gamma. And this is something which is not to be expected. I mean, they're just a jumble from the Feynman diagrams. But B, C, and J, Bern, Carrasco and Johansson conjectured, or at least deduced, in fact, well, they conjectured and other people proved, that you could organize these n gammas so that if there were some group theoretic relations between the colors, you would have the associated group theoretic relations for the kinematic factors. And these just being these polynomials in k's and epsilons. And this proposal gave rise to new identities for Yangmills amplitudes that had not been discovered before. This is only 10 years ago that they did this. And, but it has another, and people subsequently proved you could do this, but they're pretty ugly actually when you try and do it. It's sort of not, but you can do it. This actually works. And, well, why would you? Well, first of all, there's a guess that there is some sort of Lie algebra associated with the kinematics here, the n gamma, and nobody's actually identified that yet. It's been going 10 years. The original paper has 1,000 citations or something, but it still hasn't been discovered. But the payoff is that if you want to do your gravitational scattering, you can take these n gammas and you just double them up. And so you multiply them both together, and you see what I've done is I put the polarization vector for gravity as two of these epsilons, as if they had each come from a Yang-Mills field, and there you go. That's meant to be the gravitational amplitude. And they proved that if you had those group theoretic relations, this is correct for gravity. So this is something that you can prove. It's completely true at tree level. Bern, Carrasco, and Johansson have used this to compute loop amplitudes up to 4 loops systematically this way, and then 5 loops by kind of not quite getting it right, but looking at the errors. But they basically this is the only game in town for the multi-loop calculations that these people are doing. You find that this is not just a statement about plain Yangmills and plain gravity, it's a statement about a whole great variety of theories. And it is a fascinating thing. You can do it for nonlinear sigma models, for Dirac, Born-Infeld, you can do it for all your favorite supersymmetric theories, or even ones you don't like, and so on and so on. Okay, so that's a double copy story. Just to give you an example, which is as far as I'll get in this talk, at 3 points, you write down the trivalent diagram just straight out of the action from A wedge F in Yangmills, and it looks something like this, very simple. You write down the corresponding thing for gravity, and it splatters all over. I mean, it really goes all over the page. I mean, all over many pages. But on shell, this is a true statement. So very, very non-trivial statement, even at 3 points. So what I'm going to talk about today then is how to extend this to curved space. And we've got to face various issues here. So how do we define what we mean by a momentum eigenstate? And things like what's the momentum, what's the polarization vector, and so on. And then once we've done that, how is it we expect gravity and Yangmills to be related? So what I want to do is I want to do all of that through the microcosm of the plane wave spacetime. So I'll use the kind of simplest form here, which is this Brinkman form. I understand that George gave you an excellent primer on all of these things this morning. So okay. Well, you will see hints of Rosen in the background, but I won't talk Rosen. So basically, you've got a function of u, and it's a quadratic function of x, and you've got a function of u. So this is a different coordinate system to what George did. But this h is really curvature, and so you can really put it into a sandwich wave form, and you can think about scattering through that plane wave. You've got an in region and an out region, and then a non-flat region. What happens when you go through that, when you propagate fields through that region? There is a novelty here, so Roger must have pointed this out 50-something years ago, that this space-time is not actually globally hyperbolic. And so you'd actually worry as to whether it makes sense to study scattering on that space-time. And we'll see later that it does, that this failure of global hyperbolicity is not severe enough to, I'll talk about it in a moment. Okay, so that's a scenario, in region, out region, sandwich plane wave with some curvature where this h is non-zero, but otherwise it's zero in the in and out region. Okay, so if you're going to define momentum eigenstates, you're going to have, what do you mean by momenta? These are eigenvalues of symmetries, so you've got to understand what the symmetry group is. And it goes way back, the fact that the symmetry group of plane waves are as large as, pretty much as large as could be without it being homogeneous. And it's a 2D minus 3-dimensional Heisenberg group. So you've got a special one which is just in the v direction, and that's the center. And then you've got 2D minus 4 ones, which are sort of in the x-planes here. And in these coordinates, so in George's talk this morning, d minus 2 of these would have been made explicit in the Einstein-Rosen coordinates. But here, none of them are explicit. They're all on an equal footing. And they're obtained by solving a second-order ODE involved in this h here. And so you have second order, so you have 2d minus 4 solutions to that. And, but we will choose a d minus 2-dimensional subgroup because that will be what leads to our concept of momentum for the linearized fields. So that'll be our E's and their inverse matrix. So George will probably already tell you that secretly I'm working in Einstein-Rosen. I'm just not confessing it properly. And in fact, the reason why you might want to work in Einstein-Rosen is because in those coordinates, the separability of the Hamilton-Jacobi equations is immediate, whereas in these coordinates, you've got to have these E's. You've got to have solved these second-order ODEs for d minus 2 of the Killing vectors. And Here now you see some shear as well appearing in the Hamilton-Jacobi separable solution, and this f actually is the metric that George would have written down, or the inverse of the metric that George would have written down. And this solution to the Hamilton-Jacobi equation is what leads to the clean-cut solutions to the wave equation on plane wave background. So you can write down the solution, which is essentially just a delta function in phi divided by this determinant here, and so that's what makes these solutions so nice. Now, what is the momentum? Well, of course, you could just think of it as being the ki's and k plus, but sort of slightly surprisingly, you also have something that you could think of as a curve momentum as well. If you take the gradient of this function phi, that gives you a covector field, which, although it's not constant, it is null. And of course, as u goes to minus infinity, this could all have just been a straightforward momentum vector that's constant. But then as u goes out to plus infinity, there will be some memory of having gone through that wave. And what you'll discover is that the flat planes that were incident on the wave, once you've gone through the once you've gone through this region of curvature, they'll be curved. And in fact, I think in general they're sort of these. They can be quite. I don't think they look like that, but they're the pieces of Dupin cyclides or cyclide. They're curved surfaces. So there's some memory of having gone through the curvature, just in the way that the momentum eigenstates get smeared out. So that's a weirdness with these things. Now. Sorry, what's his name? Sorry, I'll come to that later. We're actually going to be concerned about Yangmills and gravity, and in order to do that, we're going to need to have some spin raising. And what's nice is that we actually have lots of spin raising operators. So these are straightforwardly tensors, which are, I write down here, which are covariantly constant. And because we've got d minus 2 of them, we can write down a full d minus 2 polarization states for electromagnetism. The epsilon A, this A was a d minus 2 index, but this is a one form where we start with the solution to the wave equation we had on the previous slide, this e to the I little phi k over root e, and we can just hit it with R once to get a Maxwell field, or R twice to get linear gravity. So these would be the fields that we plan to scatter. And but what's interesting here is that again we can sort of define a curved concept of polarization. So I've got a curly epsilon and a flat epsilon. This epsilon is a bunch of constants, d minus 2 constants. This curly epsilon is a one form on spacetime, which has the shear sitting inside it. Now, when you do this second differentiation, you get two copies of the Maxwell polarization, but you also get an extra shear term. And so this is something that you could worry about as an obstruction to the double copy that arises in curved space. Just by virtue of the curvature. I was talking about the Huygens property and tails, and so Friedlander actually proves that the wave equation is the only equation on a plane wave spacetime that satisfies the Huygens principle. So if I've got these spin raising operators, what happens if you take a clean-cut solution? Well, the clean-cut solution is just meant to be one delta function of phi, or phi plus a constant or something. Now, if you want to have a delta function in the curvature for a spin 1 field, you have to do you're going to take a derivative of A there. So you have to do phi times the step function in phi. And then when you take the derivative, then you'll get a nice curvature, delta function in the curvature, but there'll also be terms where you get the step function as well. So you explicitly construct the tail for this solution. So you have a delta function, but you have a tail. And the spin 2 case is very similar. You get a tail at spin 2. Okay, so where am I time-wise? So we can play the same games for Yangmills as well. So with Yangmills, then we can write down a plane wave Yangmills potential, and of course we're going to really want it to be something in the center of the Lie algebra. So the thing itself is not very complicated. So we can do the same game. We can have a sandwich wave, and we can solve the Hamilton-Jacobi equation, but now for a charged particle. So we're really looking at charged solutions to the wave equation. And so the point here then is that although we want to think about Yangmills, we can always choose the background to be in the center well, we can't always, but we will choose the background to be in the center of the Lie algebra. And then the charge is all you've got left for another field. So if it was also in the center, it wouldn't even couple to A, but if it was if it was in some other part of the Lie algebra, then it will, and it'll have a charge which I'll call E. But more generally speaking, the E would be associated with the root of the Lie algebra. Anyway, we can play the same game as before. We'll have a curved momentum, and that will have an extra shift in it now, corresponding to this capital A. So I've written this down again in the kind of Brinkmann form. There's a Einstein-Rosen form where it's just capital A, little a, dxa. There's no du term. And anyway, so the momentum gets shifted by this capital A as you propagate through the space-time. And so with this solution then, if you choose a gauge with this in which this capital A is 0 in the past, then in the future, this capital A will generally be constant. It'll be an integral of whatever the curvature had been. And what you discover then is that the momentum will have had a kick by this capital A. So again, there's some memory of having passed through this electromagnetic plane wave. And this F dot again will be non-trivial. So okay. So we can play the same games as before then. We can think of this as, sorry, what I was trying to explain on the previous slide was that we can think of this as being valued in the Cartan subalgebra of some gauge Lie algebra, and then the colour of a particle coupled to that capital A, so this is a linear field on the background, is encoded in the charge, which is an eigenvalue of the element of the centre that this is capital A is taking its values in. And okay, so then we can we have our solution. We can we can take our charged scalar field, and we can again play our game of doing some spin raising to get a solution little a to the background coupled linearized gauge field linearized around that capital A. And as before, this spin raising operator will give rise to what you might think of as a curved polarization vector for this solution, in the sense that this curly epsilon tilde sub mu will be related to the constants you put into the to the spin raising operator, but there'll be some mu dependence coming from the shifted momentum in the solution. Okay, so what we're going to be doing, you see, is we're going to be comparing the Yangmills amplitudes that are background coupled to a Yangmills field, the Yangmills plane wave, to the gravity amplitudes that are background coupled to a gravity plane wave. So I need to have both available for this exercise. Okay, so any questions at this point? So I've constructed a whole bunch of background coupled fields on plane waves. And okay, well anyway, I'll carry on. So one of the things which I think is actually so Roger's old result then might make you feel concerned. So what does it mean when a space-time is not globally hyperbolic? It means that some of the null rays escape. Not all of the null rays are captured by, you don't have a Cauchy hypersurface. So if you're foliating your space-time by hypersurfaces, then you're necessarily missing some of the light rays, and there could be some leakage. Some of the information of the solution could run off. And so how would you detect that? Well, you would detect that in really just in a two-particle function. You just take the inner product, and you might discover that the inner product is not independent of the choice of hypersurface. So in fact, I'm going to be choosing a hypersurface which might look a bit dangerous anyway, because I'm going to be doing we had the picture of the plane wave like this, and I'm going to be using the u equals constant hypersurfaces and I'll evolve through the space-time. And so you might have thought that was dangerous anyway. I mean, I'm now really flouting the global hyperbolicity. Those aren't Cauchy surfaces. But the point is that if you take these momentum eigenstates and you look at their norms, they are U independent. For spin 1, spin 2, you get the right formulae for the norms, and these are momentum eigenstates, so you get delta functions in the momenta. You find that you haven't lost anything by missing out some of these null directions. And I guess my hand waving sort of reason for that is that the number of light rays that you're missing out is very small. So you're missing out all of the light rays that are traveling up the diagram here. They're the light rays in the geodetic shear-free congruence, and the d by dv direction in the coordinates. And that set of light rays has high codimension in the space of all light rays. And so if you're working with L2 objects, then you can't have a distribution supported. You can't have a normalizable distribution supported on anything of that codimension. So somehow the failure of global hyperbolicity doesn't stop you from discussing scattering. Okay, so let's carry on then. And actually, sorry, I haven't kept track of time. When was I meant to stop?
Well, so according to the schedule, we should stop at 10 past 5.
Okay. I'll aim for that. No, it's okay. You've all had a long day, I can tell. Okay. Anyway, okay, so 3 particle amplitudes. So 3 particle amplitudes are sort of easy because you just read off the vertex from the action. So this is, you expand out the gravitational action to third order. And, well, what you do have to remember, though, is you're keeping the background in this. So this is maybe a little bit euphemistic because I've only kept the third order linear theory, but you have to remember that these Ds are maybe covariant Ds. I haven't written that way. So this is the cubic part of the action expanding around a plane wave. And you can insert the states that I got, that I described, and you get a formula which has some exponential factors. You can integrate out an awful lot of stuff. Because you've got the symmetries, you can certainly integrate out all the x's and all the v's. And they will give you some nice delta functions. But integrating out the u is something that you don't expect to be able to do because you had an arbitrary function in the u in the metric. But anyway, so you can boil it down, putting in our three states, h1, h2, h3, into an expression where you have, in some sense, already sort of tried to do the best you can in terms of the double copy framework. So that is to say that our gravity linear fields, you put polarization vectors that are both the same, and you can try and follow through the factorization as much as possible as you might have had in flat space. And so what you get is something which looks like a kind of a Yang-Mills amplitude squared, but now in the these curved polarization vector and momentum vectors. But you also get an extra term here, C, and this C is really associated with the tail terms of the gravitational fields. So we already saw something a bit like that when we were just doubling up a Yang-Mills field or electromagnetism on a plane wave background to gravity on a curved background. So this is what you get for squaring up the Yang-Mills field on the curved background, but there is an extra term. So the double copy is sort of failing if you think about it in that way. But the double copy wasn't really a statement about, it wasn't something that you necessarily expected to work on a curved background. What the claim was that the whole Yang-Mills theory double copies to the whole of gravity. So in fact, what we should be doing, or where we should be looking for the double copy, is in doing a three-point scattering process on a Yang-Mills background and seeing if we can double copy that to give a three-point scattering process now on a gravitational background. So you can look at the three-particle, three-point Yang-Mills amplitudes as well. And as I say, you get a term which looks like the flat case model, but in the curved epsilons and k's. But then if you write them out in terms of the kind of constant epsilons, then there is a memory term in there, and there is a tail term in there. And really what we're going to try to do is we're going to try to see that if you decompose it in this way, that the double copy works by doubling this and doubling that C. And this, so doubling the tail, that is. So the rule that we're going to come up with then is to flip charges. So you have a kind of something that looks like the flat case plus something which is this curved correction, C. If you flip the charge, then you have a F minus C, and then we're going to say that if you want to do the double copy, you should in some sense do A times A tilde, and that will give you the F squared minus C squared. And then we still need non-local replacement rules, because this double copy was a statement in momentum space, not in space-time. So we expect to have non-local replacement rules. So we have replacement rules then for the Ks and the epsilons, and then the idea is then that with these rules, then you can resurrect a version of the double copy of the Yang-Mills integrand to the gravitational one that incorporates the tails. So somehow the double copy of the A's and the Yang-Mills tails will give us the shears in the gravitational ones. Okay, so this is a little bit sort of this was a collaboration with Tim Adamo and Stefan Lefevar. So Tim's very good at operationalizing, as he likes to term it, various things, and this is doing that. So then you can ask the question as to how much further can you take these ideas. And now we are doing conventional amplitude calculations on a curved background, that is already tough. You discover that the literature does not have an awful lot of that out there. So for example, the Feynman propagators haven't actually appeared much. At least you find that the laser physicists have done some of this on a Yangmills plane wave. And anyway, so you can use these Hamilton-Jacobi momentum eigenstates to write down a scalar Feynman propagator, and you can do that on both Yang-Mills plane waves and on gravitational plane waves, and then again you can sort of spin raise these propagators, and so for spin 1 though you have this extra curvature term in the linearized field equation, and that gives rise to some propagator here. But you can solve for everything. And in the gravity case, you get a much bigger matrix here. And but we haven't yet been brave enough to calculate the gravity 4-point amplitude. This is, DeWitt famously covers some large number of papers in his pages in his 1960s papers calculating the 4-point gravity amplitude back in the 60s, sort of 20 pages or something to writing out the 4-point amplitude. I mean, what's remarkable there is, of course, the answer sort of boils down to a compact formula on one line, but the intermediate steps are huge. So we have to try and do some of that. So the test that we tried to sort of develop then was to start with the Yang-Mills case and look at this possibility of constructing these BCJ numerators at 4 points. And so can we reorganize our 4-point background coupled Yang-Mills amplitude into color kinematic form so that the kinematic factors behave this relation? And I'm not going to go through the details now. We've worked through it, and we have a paper that does appear. I forgot to put the citation up, but it's this is naively obstructed on the plane wave. But again, you can somehow operationalize, as Tim would put it, and you can find some extra mapping on the scalar propagators, and you can get some color kinematic claim that survives in curve space. Okay, so I mean, I'll stop there because the formulae, if I was to sort of try and give you the full details of that, then the formulae would start splattering rather large. So just to conclude then, we can now write out, given that we've got all the propagators and stuff, we can write out Feynman rules explicitly on plane waves. Manifesting the double copy systematically is still sort of beyond us. I mean, it's something that's local in momentum space, and so it is necessarily non-local on space-time. And so the integrals over U are something that's difficult. We in some sense, they would need to turn into some kind of convolution, which we certainly haven't managed to do. Anyway, so there's a non-trivial double copy at 3 points, work in progress at 4 points, and so these provide some first steps towards a nonlinear double copy. I mean, there are many other people trying to look at where the origins of double copy ideas are in fully nonlinear theory. I think we're still a long way from seeing that, and this is just one avenue. For us, the main point of this project was actually to provide data that simply wasn't out there in the literature. So we were we were doing ambitwistor string calculations at 3 points, and we wanted to know whether they were correct. So they were much easier actually than these, but they are correct. So these formally do verify our ambitwistor string computations, and it's the ambitwistor strings that are really manifesting the double copy. So I sort of feel that, in fact, the best way to understand it will be via the ambitwistor string version. And just in a separate project with a new research student, Atul Sharma, we've been working on cosmological backgrounds as well to try and execute some of these ideas because of an observation that the de Sitter space, in some sense, is a double copy of the one instanton, and so you can use some integrability ideas to feed this all. Anyway, so that's it. Thanks very much, and happy birthday. You know, so.
Questions, comments? Krzysztof.
What is the actual status of 5 loops? Because there was this ambiguity whether it's 24 divided by 5 or 26 divided by...
Five. Well, okay. So I mean, Zwiebern is always upbeat, but 5 loops is done, and it failed.
But what went wrong? The integrand or the integral?
So I guess the point is that what they do is they use all of this to get an integrand, and then once you boil down the integrand, you look at the dangerous ones, and you examine the coefficient of the dangerous ones, which are going to provide new ultraviolet divergences. And they found that those coefficients were not 0. But Zvi has a story about this. I think he's lost his bottle of wine. Kelly Stelly gets his nice bottle of Californian wine. But there's a claim that there's a sense in which these are sort of what Zvi would call evanescent divergences. So, of course, sorry, by the way, this is a discussion about n equals 8 supergravity, whether it's really finite or not, whether it's really infinite or not. And, of course, the whole agenda in the 80s was to say that you need string theory. I'm sorry, you know, n equals 8 is no way to regulate your theory, and they were trying to sink n equals 8 supergravity. I mean, you may have disliked it for other reasons, but I mean that was the main aim of people at that time. And so Zvi was trying to be a naysayer and say, well, you didn't prove it, you just showed that your techniques didn't make it finite. And I think that remark still holds. So because they were saying originally that there were singularities at ultraviolet divergences at 3 loops and 4 loops and 5 loops, and then they honed down their methods and they said, oh, but there will be one at 7 or something. Anyway, so Zvi's trying to say that, yes, they might be singular, but maybe we can keep track of them all. Maybe it's all just coming from these topological diagrams.
But the conviction that it's still a double copy of Yangmills is still there, or it isn't?
Well, the double copy, I guess, you see, these people are pretty hands-on, and what happened was that they had simple ansatzer for constructing these kinematic numerators. And the key point for them was that once you've got a set of these numerators for one master diagram, you've essentially got them for all diagrams. That was what the magic was. And so at 5 loops, the cheap ansatzer they had were no longer working. And so they had to sort of start examining the differences between something that was perfectly color kinematic and what it was that they could construct.
Let us thank Lionel again.